Right, ready to dive into a paper attacking a pretty massive challenge in AI. It's all about how we handle these super long sequences of information.
Oh, yeah, those really long ones?
Without our models basically just choking on all the data.
Yeah.
Like, think about it, processing huge code bases, giant documents, or even like chatbots that can actually hold a conversation for hours.
Right.
And remember what you've talked about.
Exactly. It is a problem that's been holding us back, for sure.
Yeah.
Traditional attention mechanisms just weren't really built for this kind of complexity.
Exactly. And it's a problem that's honestly only getting more pressing as we're building these increasingly ambitious AI systems.
Right.
So what's the solution?
What?
Well, the authors of this paper are introducing something called NSA.
Okay.
It stands for Natively Trainable Sparse Attention.
Catchy.
Catchy, right?
Yeah.
But basically, they've found a way to make attention way more efficient by focusing only on the most important information.
That's the key insight here, sparsity. So instead of trying to analyze every single connection in a massive sequence, NSA kind of strategically ignores the less important bits.
Okay.
It's like a super smart speed reader
Yeah.
that can pick out the key sentences while still understanding like the overall meaning of a whole book.
Okay, so it's speed reading for AI.
Yeah, you could say that.
But what makes NSA really stand out is that it's trainable from the ground up.
Right.
Which means we can actually teach it to focus on the right information for a specific task.
Yeah, and that's a game changer because it means we can train these massive models on incredibly long sequences much more efficiently.
Right.
Opens up a whole world of possibilities for new and more powerful AI applications.
Now, before we really get into the nitty-gritty of how NSA works,
Okay.
let's quickly recap why attention is so important in the first place.
Okay.
For those who haven't been living and breathing transformers,
Right.
what's the deal with attention and why does it struggle with these massive inputs?
So imagine you're reading a research paper. You don't painstakingly analyze every single word, right? You skim, you highlight, you focus on the key sentences and paragraphs. And that's basically what attention does for AI models.
Yeah.
It helps them figure out which parts of the input are the most relevant for a given task.
So it's like finding the signal in the noise.
Exactly.
But the problem is, as the input gets longer,
Right.
like going from a paragraph to a whole encyclopedia,
Yeah.
the number of possible connections between words just explodes.
Right.
And traditional attention tries to analyze all of them.
Exactly. And that's where the computational cost comes in. The more connections you have to analyze, the more time and resources it takes. It's like trying to keep track of every single thread in like a massive conspiracy theory.
Oh, yeah.
It quickly becomes overwhelming.
Yeah, and that's where NSA comes in, right? It's all about streamlining that process, being more selective about which connections to analyze. So how does it actually work? Walk us through the magic.
Well, the authors call it a dynamic, hierarchical, sparse strategy, which sounds complicated.
It does?
But is actually quite elegant.
Okay.
Think of it as having two levels of speed reading.
Okay.
First, you quickly summarize each chapter to get the gist of the book.
Okay, I'm with you. So we're compressing the information into more manageable chunks.
Right.
Got it.
And then based on those summaries, you zoom in on the key sentences within the most important chapters for a deeper understanding.
Oh, I love that analogy. So how does NSA do this summarizing and zooming in a technical sense?
So it all boils down to three key pillars: token compression, token selection, and a sliding window.
Okay.
Token compression is like creating those chapter summaries.
Okay.
NSA groups the input tokens into blocks and creates a compressed representation for each block.
Okay.
Capturing the essential information.
So it's reducing the number of tokens the model needs to handle making things faster.
Right.
But how does it decide which chapters to focus on?
That's where token selection comes in. Based on this compressed representations and the specific question the model is trying to answer.
Okay.
We call this the query.
Right.
NSN calculates important scores for each block,
Okay.
figuring out which ones are likely to contain the most relevant information.
So it's like saying, hey, these chapters seem really important for this particular question. Let's take a closer look.
Precisely. And then it selects a subset of those blocks with the highest important scores and goes back to analyze the individual tokens within those selected blocks.
Okay.
This ensures it's not just throwing away information randomly, but making informed decisions about where to focus.
Okay, that makes sense. So we've got compression and selection working together.
Right.
What's the sliding window all about?
So the sliding window is like having a spotlight that focuses on the most recent tokens in the sequence. This helps the model maintain awareness of the immediate context,
Okay.
making sure it doesn't get so caught up in the long-range patterns that it misses crucial local information.
So it's like keeping an eye on the details while still seeing the bigger picture.
Exactly.
That's clever. So we've got compression, we've got selection, we've got a sliding window.
Right.
How do all these pieces fit together to actually perform the attention operation?
So NSA uses these three techniques to generate three sets of keys and values.
Okay.
One for each pillar.
Got it.
These are then used to compute attention scores for each query.
Okay.
The final output is a weighted combination of the results from these three branches, with gate scores controlling the contribution of each branch.
Wait, gate scores, what are those?
Think of it like a chef adjusting the proportions of different ingredients in a dish to achieve the desired flavor.
Okay.
The gate scores are learned during training.
Okay.
So the model can figure out the optimal balance between compression selection and sliding window for different tasks.
So it's like a dynamic recipe that adjusts itself based on what's being cooked.
Exactly.
Got it.
It's all about finding that sweet spot between efficiency and accuracy.
This is all starting to sound pretty impressive, but I have a feeling we're just scratching the surface here.
Yeah.
There's a lot more to unpack, especially when it comes to the actual implementation and the results they achieve.
Yeah, definitely.
But that's a story for another time.
For part 2.
For part 2, stay tuned, folks. This is just the beginning of our deep dive into NSA.
Yes, it is.
And trust me, you won't want to miss what comes next.
Welcome back, everyone.
In part 1, we explored the really ingenious design behind NSA.
Yeah.
And how it tackles that challenge of scaling attention for those super long sequences.
Right.
But now it's time to see if this thing actually delivers on its promises.
Yeah, let's get into it.
So let's dive into the experiments.
All right, get ready for some impressive results. The authors really put NSA through its paces.
Okay.
They started by pre-training a massive model with a whopping 27 billion parameters,
Whoa.
both with full attention and with NSA.
Okay.
This was crucial to demonstrate that NSA's efficiency doesn't come at the cost of performance, even at scale.
27 billion parameters, that's getting into the realm of like those state-of-the-art language models we hear so much about.
Right.
And pre-training is like giving the model a crash course in language, right?
Exactly.
Exposing it to a massive amount of text data so it can learn those fundamental patterns.
Exactly. It's like laying the foundation for everything that comes next.
Got it.
So once they had their pre-trained models, they tested them on a battery of benchmarks.
Okay.
Starting with general language tasks.
Okay.
We're talking things like question answering, text summarization, even translating languages. These are the bread and butter tasks that any good language model should be able to handle.
So how did NSA fare against the traditional full attention model in these standard tests?
It actually performed remarkably well.
Okay.
In most cases, it achieved comparable or even better performance than the full attention model, despite being much more efficient.
Wow.
This was a strong indication that NSA wasn't sacrificing accuracy for speed.
That's a big win right there.
It
But the real test, the one we've all been waiting for, is how NSA handles those super long sequences, right?
Right.
That's where it's supposed to really shine. What did the authors do to push NSA to its limits?
So they turned to a benchmark called long bench,
Okay.
which is specifically designed to test a model's ability to handle really long sequences. Think like understanding documents that are hundreds of pages long, answering questions that require pulling information from different parts of a massive textbook,
Oh, wow.
or even analyzing code bases with thousands of lines of code.
Now, that's what I call a challenge. It's like asking the model to read War and Peace and then answer detailed questions about it.
It is, and NSA rose to the occasion. They compared it to a bunch of other state-of-the-art sparse attention techniques,
Okay.
and NSA came out on top, even surpassing the full attention model in some cases.
No way. So even with a limited attention budget, so to speak,
Right.
NSA was able to zero in on the most important information and make more accurate predictions. I'm impressed. Did they have any specific tests that really highlighted this ability?
Oh, absolutely. One that really stood out was the needle in a haystack test.
Okay.
Imagine a massive document, like a giant encyclopedia,
Right.
and you're trying to find one specific fact buried within it.
Okay.
This test is all about seeing how well a model can extract a tiny piece of information from a vast sea of data.
That sounds incredibly difficult, even for a powerful AI. How did NSA manage?
It did remarkably well. Even with a context length of 64,000 tokens, that's like an entire novella, NSA was able to find the target information with perfect accuracy.
Wow.
Regardless of where it was hidden in the document, this really demonstrates the power of that hierarchical approach,
Yeah.
combining a quick scan to identify the most relevant sections with a laser focus on the crucial details.
It's like having a detective who can skim through thousands of pages of evidence and instantly pick out the one clue that solves the case. Okay, so we've seen that NSA can handle general language tasks, long sequences, and even find those needles in haystacks.
Right.
But there's one more area I'm really curious about, its ability to reason. Did the authors test that?
They did, and this is where things get really interesting.
Okay.
They wanted to see if NSA could perform what's called chain of thought reasoning,
Okay.
which is basically the ability to solve complex problems step by step like we humans do.
So instead of just giving an answer, the model has to explain its thought process, showing how it arrived at the solution.
Exactly. This is important for tasks that require logical deduction, like solving math problems or writing code. They focused on mathematical reasoning using a challenging benchmark based on the American Invitational Mathematics Examination,
Okay.
or AIM for short. This is a high school level math competition with some pretty tough problems.
Okay, so they're basically seeing if NSA can H a high school math test. I'm on the edge of my seat here.
Well,
what were the results?
They fine-tuned both the full attention and NSA models on a data set of mathematical reasoning traces.
Okay.
These traces basically show the step-by-step thought process involved in solving the AIM problems.
Okay.
It's like giving the models worked examples to learn from.
So it's not just about knowing the formulas, it's about learning how to apply them logically.
Exactly. And the results were pretty remarkable. NSA significantly outperformed the full attention model, demonstrating a much stronger grasp of the logical steps required to solve these complex math problems.
So not only can it handle language, it can actually reason.
Yeah.
And do it better than a full attention model. That's mind-blowing.
It is.
But I guess it's not all that surprising considering the efficiency we've already seen. Did the authors actually measure those speed improvements? I'm dying to know the numbers.
They did, and the numbers are pretty eye-popping.
Okay.
They tested the models on a multi-GPU system.
Okay.
And found that NSA achieved up to a 9x speedup in both the training and decoding phases.
Ooh.
Especially as the sequence length increased.
9x faster. That's huge. I can only imagine the impact that could have on the time and resources required to train these massive models.
It's a game changer for sure, and it means we can start to tackle even larger and more complex problems that were previously out of reach.
This has been an incredibly insightful look at the experimental results. It's clear that NSA is not just a theoretical improvement, but a practical breakthrough that could significantly advance the field of AI. But what about the bigger picture? What are the implications of this technology? How could it change the way we develop and use AI in the future?
That's the really exciting part. And that's exactly what we'll explore in part 3. We'll delve into the potential applications of NSA in fields like natural language processing, code generation,
Okay.
and even scientific discovery. So make sure to join us for the final part of our deep dive,
Yes.
where we'll let our imaginations run wild with the possibilities.
Welcome back to the final part of our deep dive into NSA. We've journeyed through all the technical intricacies.
Yeah,
We've witnessed some pretty impressive results.
absolutely.
And now it's time for the grand finale, exploring the possibilities.
This is where we get to unleash our imaginations and see where this breakthrough could lead us in the world of AI.
Exactly. We've seen how NSA can handle those massive novels, complex code bases, and even reason like a high school math miss.
Right.
But let's zoom out for a second and consider the broader landscape. Where could this technology really make a difference?
Well, one area that immediately jumps out is natural language processing, or NLP.
Yeah.
Imagine chatbots that can hold genuinely engaging conversations over extended periods, remembering the context and nuances of your previous interactions.
Right.
No more of those frustrating loops where you have to repeat yourself every few minutes.
Oh, yeah.
Ugh.
It's like finally having a chatbot that feels like you're talking to a real person, someone who actually remembers what you said earlier in the conversation.
Precisely. And this goes beyond just chatbots.
Okay.
Think about virtual assistants that can understand and execute complex multi-step instructions.
Yeah.
You could say, hey, plan my dream vacation considering my budget, my travel style, and my dietary restrictions.
Right.
And it could actually pull it off, taking care of all the details.
No more endless hours browsing travel websites. I'm already sold.
Yeah.
What about creative writing? Could NSA help us generate more compelling and intricate stories?
Absolutely. One of the big hurdles with current language models is that they tend to lose the plot when generating longer pieces,
Yeah.
repeating themselves or introducing inconsistencies.
Right.
NSA's ability to maintain focus over long sequences could be a game changer for authors, screenwriters.
Okay.
Anyone who loves crafting captivating stories. We could see novels, screenplays, even entire series with a level of depth and coherence that's hard to achieve today.
That's a pretty exciting prospect.
Yeah.
Speaking of complex systems, what about scientific research?
Oh, yeah.
I can only imagine the potential there.
Imagine being able to analyze the entire body of scientific literature on a specific topic,
Okay.
not just a handful of cherry-picked papers.
Yeah.
NSA could empower researchers to uncover hidden connections, spot emerging trends, and generate hypotheses that would have been impossible to conceive with traditional methods.
Right.
It's like having a research assistant who's read every single paper in your field and can synthesize all that information in a meaningful way.
Talk about accelerating scientific discovery. It's mind-blowing. But let's shift gears for a moment.
Okay.
We've talked a lot about the positive potential, but are there any potential downsides?
Yeah.
Any risks or ethical concerns that we need to consider as this technology matures?
That's a crucial question and one we can't afford to ignore.
Yeah.
Like any powerful tool, NSA has the potential for misuse.
Right.
One concern is the possibility of generating even more sophisticated deepfakes or spreading misinformation through highly convincing text generation. It's a reminder that we need to develop safeguards and ethical guidelines alongside the technology itself.
Absolutely. It's not just about building powerful AI. It's about ensuring that it's used responsibly and for the benefit of humanity.
Couldn't agree more. It's an ongoing conversation that requires collaboration between researchers, policymakers, and society as a whole. We need to be mindful of the potential consequences and proactively address any ethical challenges.
Well said. So looking ahead, what are some of the key research directions that you're most excited about in light of NSA's breakthroughs? What are the next frontiers?
One avenue I find particularly intriguing is exploring whether these sparse attention principles can be applied to other AI architectures beyond transformers.
Okay.
Could we see similar efficiency gains in convolutional neural networks, for example, or even in entirely new types of models that we haven't even conceived of yet?
It's like NSA has opened a Pandora's box of possibilities. What else has piqued your interest?
I'm also fascinated by the potential connections between these artificial attention mechanisms and how attention works in the human brain.
Okay.
Could studying biological systems provide insights that lead to even more powerful and efficient AI models?
Interesting.
It's an exciting area of exploration that could blur the lines between neuroscience and artificial intelligence.
It's like AI research is coming full circle, drawing inspiration from the brain, and now potentially offering insights into the workings of our own minds. It's a truly remarkable journey.
Indeed, and it's a journey that's just beginning. Who knows what amazing discoveries lie ahead?
Well, on that note of endless possibilities, I think it's time to wrap up our deep dive into NSA. We've covered a lot of ground.
Yeah.
From the technical details to the potential impact on various fields. But more importantly, I think this paper highlights the power of human ingenuity and the relentless pursuit of innovation in the world of AI.
Right.
It's a reminder that we're living in an era of unprecedented technological advancement, and the future is brimming with exciting possibilities.
It's been a truly exhilarating exploration, and I hope our listeners share our enthusiasm for this groundbreaking work.
Yeah.
NSA has the potential to reshape the landscape of AI, and it's going to be fascinating to see where it takes us in the years to come.
To all our listeners out there, stay curious, keep exploring, and who knows, maybe you'll be the one making the next big breakthrough. Thanks for joining us on this deep dive into the world of NSA.